So let me then get started and recall our goal for today is to sketch a proof of this theorem that any D-maximal Hardy field is H-closed. H-closed being just an abbreviation for being Newtonian omega-free Liouville closed. So a model of our complete theory of H fields. And D-maximal, remember, is simply a generalization of maximal. It means it has no differentially algebraic Hardy field extensions, but it might have other differentially transcendental Hardy field extensions. Okay, so I still need a few more preparations to get to this point. So I first want to remind people of some analytic things, well known. So a reminder about smoothness. In fact, Patrick yesterday hinted at one of those things. Reminder about smoothness of solutions, of ODEs, of algebra, yeah, of right. So that is simply the following. Well, oh yeah. First, some notation for R, a differential ring. Yeah. And P, a differential polynomial. P one indeterminate. We define the separand SP y. It's, well, simply the formal derivative of P with respect to the, oh, I have to say here of order R, It's the formal derivative of P with respect to the highest derivative variable occurring, yeah. So this is again in this ring. It's is of order at most R, but the degree in YR is smaller. And so something degree of the separand is less than, well, the degree in the variable YR of SP is less than the degree of P in YR. Since we are assuming that P is of order R, this degree here is positive, YR really does occur. Let me just give an example to see how simple how simple it is to compute the separand, and I'll get to the role of the separands. Let's say Py is simply y squared plus 2y prime y plus y prime y double. I'll just write something pretty random, y double squared, right? And now you have to take this is of order 2. Since y double is the highest derivative occurring, and so to get a separand, you have to take the derivative with respect to y double. So the separand, well, you only have to look at the terms where y double actually shows up. And so you take this term and its derivative, when you consider y double as a variable, is y prime plus, and then here you get 6y double. right? So this is very elementary. And I also want to remind you that these are the germs that are R times continuously differentiable for every R. Yeah? So the intersection over all R of CR. And unlike the CRs themselves, this is a differential ring with respect to the ordinary, taking the ordinary derivative, right? And of course, it also contains certain distinguished subrings, only the germs of the infinitely differentiable functions, and that in turn contains C omega, which are consisting of the rings of the real analytic functions at all germs at plus infinity, right? And now I can state an important fact, very classical. Or, I mean, it's certainly a consequence of very classical facts. Let's say we have a differential polynomial now with coefficients in here, right? So see, for example, if P has coefficients in a Hardy field, that is the case, and so say it has order R, yeah. And let F be an element of CR, which you can plug in, therefore, if you have a differential polynomial of order R and you have an R times continuously differentiable function, then it makes sense to substitute F for the indeterminate Y here, and suppose that it's 0. Yeah. Then, well, so this is sort of the minimal assumption that for which PF makes sense. But if this happens, it turns out under one extra assumption, namely that the separand evaluated at F is a unit, that this function or that this germ is in here, right? So if PF, the separand of P, evaluated at F is okay as a unit, right? It's a continuous germ, of course, and a unit means that it is never 0. It's equivalent to being, sorry, not eventually not 0. Eventually not 0 is then F is actually in C, right? So you get this for free. Yeah, and similar things hold if you assume that P has coefficients in here. And then with the same assumptions, F will also be in here. And likewise, if the coefficients of P are in here, and again, the separand is eventually non-zero, then F will also be in here. So you get this, you see, because we are going to construct solutions of differential equations, which a priori we only know lie in here. But of course, if we wanted to have them in a Hardy field, to lie in a Hardy field, we need to know, we better be sure that they are actually in here. And so this gives some kind of reassurance that we are not out of line here. Yeah, and another remark I want to make is that all this is also true when you go to the complexification. So of course, you can join I here. And you can assume this, and you can assume, let's say now that F is also complex, then again, if the separand evaluated at F is eventually non-zero, then F is in here. And likewise, when the coefficients of are in here or there. So all this is very standard things. Well, actually, the complex version of this, I did not actually find a reference for that in the literature. And the real version is sure that follows from where things that that are recorded in the literature. For this complex version, it's true, but you need to do a little work, extra work to get that. And the complex version is also needed. But now, also I want to mention a relevant special case. Because for us, the relevant special case is, you see, we are going, ultimately, when we want to solve these algebraic differential equations, we can reduce to the case that the degree 1 part of our differential polynomial is sort of dominating all the rest. Yeah. And so that means basically that we are dealing with the following. Yeah. So here Py, again, Py is now an element of, So here, I'm now H a Hardy field. And now Py has coefficients in H, so in particular in here. And of the form, well, I'm going to basically writing a linear degree 1 part, the degree 1 polynomial, differential polynomial, Fry, and then followed by something, a remainder, and where R, well, I'm only interested in the part of R that has degree greater than or equal to 1. So I'm removing from R the constant, the R0, the R sub 0, the degree 0 part, and I'm left with the degree greater than or equal to 1 part, and I assume that this is small. Small compared to this part, because here we have a coefficient 1. I don't care how big the f's are, but I know that this coefficient is 1, and I want my to make sure that this remainder part is small. What do I mean with this notation? Since R is, of course, a differential polynomial and not an element of H, I mean all the coefficients of i.e. all coefficients which are elements of H of R greater than or equal to 1, R infinitesimal, right? Okay. So, and suppose now, if F is now a solution of our equation, if F in CR, Pf is 0, but now I make the extra assumption that F and all its derivative up to order R, well, that's all I can take, are bounded. No, actually, yeah, do I mean bounded or infinitesimal? Let me see. No, yeah, this is okay, yes. Bounded is enough. Then, in fact, if you look at the separand, what is the separand of this differential polynomial? Well, you take the derivative with respect to yr. Oh yeah, I didn't say that this is of order R, but that means that capital R is also of order at most R, since here we have already. So this gives you, for the separand, term 1, and here yr doesn't appear. Here it might appear, but it will only appear with coefficients that are infinitesimal. And since you also plug in only f and its derivatives that are bounded, that means that the separand will be 1 plus what you get from this, and it will be infinitesimal. So that means that SPF will be asymptotically equal to 1. Right? So in particular, it's a unit. SPF is actually a eventually non-zero. And so then we get the conclusion that F is in our ring C less than infinity. Right. And all that is also again true for the complexification. Yeah. So in other words, if you work over the complexification, the coefficients are now in HI, and right, okay, of course, you extend the valuation to HI in the derivation as well, and that all makes sense. And then F can also be in the complexification, and all this, well, this will be then in here, and the conclusion will be also right. So all this, and likewise for the C infinity and C omega versions of this. Right. Okay, so that is one preliminary that I wanted to take care of. Because then we don't have to worry anymore about our solutions that we are constructing, which are in CR. They will automatically be in these much smaller C less than infinity rings. Okay, the next preliminary is a bit more work. Inverting. I want to inverting linear differential operators. Yeah, please ask questions or interrupt me if anything is operators. Right. Okay, so I want to, yeah, so here we actually have to go to yeah, here I work with germs, right? But now I want to actually work with actual functions, since CRA, what is that? Is the, well, it's a ring actually, but most relevant is that it's an R vector space, R linear space of all the CR functions from A real valued functions defined on this half line, but including the number a. Right. So yeah, there are technical reasons for wanting to include this a here. Right. And right, because we want to make this into a Banach space. Well, once we restrict to bounded functions sufficiently, yeah. Okay, so if R is 0, I often omit the superscript 0, right? So let phi be just for the moment just continuous function on this interval, and then we'd like to invert the R linear operator, R linear map or operator. Well, let me write it as delta minus phi. It's from C1a, from 1 times continuously differentiable function to C0a. And what does it do? It takes such a function and it's, well, this means take the derivative and this means multiply by phi. So it's f prime minus phi f. Right. Yeah. Also, let me make it maps for r greater than or equal to 1, it maps CRA into CR minus 1a. Yeah? Since we take a derivative here, provided phi is at least r minus 1 times continuously differentiable if, so for phi at least r minus 1 times continuously differentiable, right? Okay, so I can actually write down explicitly a right inverse to this map. Yeah, I see now that I think I should, well, I can still write here. It's a little, a right inverse is a right inverse. That's it. Right inverse of delta minus phi is given by, well, let me denote this operator by B. So it depends on phi, and it's okay. So of course it's a right in, it goes the other way, C0a to C1a is given by B is B phi, where B, and I'll write down the formula. So if you take a continuous function on this half line, and to evaluate it at t, what do you do? Okay, and this comes perhaps a little bit out of the blue, but integral a to t e to the power minus phi s, and I'll say what phi is, f gs ds. Integrate from a to t with respect to the, yeah, right. Where phi, well, it's, of course, it's not too surprising that to invert a differential operator, you have to integrate, right? Since integration is, after all, inverse to differentiation. But where phi is where phi t is itself given by an integral, namely phi s. Yeah, this is big phi and this is little phi. Yeah. In other words, this is just an antiderivative of little phi with the initial condition capital Phi at A is 0. Right. Yeah, you could simply, in what sense do I mean, in what sense is this the right inverse? Well, if you first do B and then apply this, you get the function you start with back. So, so delta right inverse just means what you think it means, delta minus phi applied to BG equals G. Yeah. Okay. Yeah, so that is, yeah, you could, I mean, this is not too hard to check if you look at it the right way. I mean, in some sense, this is just a, if you look at this, you see that this is sort of a twist of the ordinary integration. As you would expect, right? This is a kind of a modification of the ordinary derivation, and so you also expect some kind of modification of ordinary integration, and that is the twist you have to apply. Right. Now, this operator B has, let me see, has sometimes good properties, but not always. So, in fact, this is not the only this is not the only right inverse, but of course it's certainly linear. It's again a linear map, R linear map, but we want more. Right. Okay, so let me say this. If phi happens to be less than or equal to minus epsilon on A comma plus infinity, this B has good properties. This B has good properties, and I want to explain that. So to explain this, I need to introduce a subspace of CRA to explain. Yeah, define the following subspace RA bounded. Yeah, I want to see CRA is too big a space of functions to be, but I'm going to restrict to those that are bounded in the following strong sense. Not only F, but also all its derivatives up to order R are bounded. And you can imagine why I included A as an endpoint here, because of course that means that bounded is the same as eventually bounded. And that wouldn't be the case if I didn't include that endpoint. Okay, right, but the thing is that you can put a norm on this subspace, this R linear subspace. We make it and in fact it makes it we make it a Banach space, a Banach space in sort of obvious fashion. I mean, this is with norm, well, let me put it, subscript R here. Of course, this norm depends also on A, the endpoint here, but I'm not going to put everything in. I don't want to make the notation too complicated. So this is the maximum of the subnorms of these functions. F prime to Fr, where here I simply mean the subnorms, right? And since they are bounded, these subnorms exist. And so this is a finite, yeah, since this is finite, and it is a Banach space. I mean, this is a well-known kind of Banach space, I would say, and is typically used also in ODE theory in various contexts. And now I want to mention the following fact. Yeah, well, let's say R is greater than or equal to 1, and phi, I'm now assuming also that it is R, at least R minus 1 times continuously differentiable and also bounded in this in that sense. Then this operator maps CR, let me see, CRA bounded. Well, of course, it's the main, as I defined it there, is bigger, but now I'm restricting it to the subspace, and then it actually maps into 0 bounded A. It maps this into there, so I'm just writing this restriction that way, and this is now a continuous operator. Yeah, so here we have a norm, and here we have also a norm. Of course, for R is 0, this is just the subnorm, and this is a continuous linear operator. It's continuous, and in fact, you can give it a bound on its operator norm. Right? If you have a linear operator between two Banach spaces, then if it's continuous, it has itself a norm, this operator, which is simply the supremum of the norms of the operator applied to elements of norm at most 1 in the domain. And in fact, you can estimate, you can bound this operator norm by 1 plus 2 to the power R minus 1 times the R minus 1 norm of phi. Anyway, it's not too important but more important is what happens to this inverse there. Also, B phi maps, of course, it goes the other way around. It maps C0 bounded into that one. Of course, it has to be proved, but it's B phi is continuous, provided, and this is an important proviso, that phi is less than or equal to minus epsilon. Phi is less than or equal to minus epsilon on A plus infinity for some epsilon, for some positive epsilon. Yeah? So provided phi is less than or equal to some negative fixed number, you can indeed show that B phi maps this back into that, and it's a continuous operator. And you can again estimate the operator norm in terms of the operator norm of phi, and also maybe epsilon, and maybe some other thing that I don't want to get into. Yes?
Why is that CA0 bounded and not C?
Why is what?
Oh, the map is going into CA0 bounded?
Yes?
Why not CAR minus 1?
Oh, wait, yeah, you're right. You're right. Mistake. This goes to R minus 1. Yes, of course. Thanks. And this goes to, yeah, that's what I meant. Yes. Thanks. I was already ahead where I take a composition of R such maps. That comes later. Right. Yes. Okay. Did I make the same mistake? And well, here, yeah, you're right. No, here I did it correctly. Right. Right. Okay, now this condition here, this is called the attractive case. Yeah, the attractive case. Yeah. I haven't really tried to find out why it's called the attractive case, but I take this terminology from Joris, and yeah, and of course, wait, now I need to find a little page that I inserted here, and where is my page that I inserted? Oh, that's, oh yeah, here it is. Right. Yeah, so of course, I also want to say something about the case where it's the opposite, which is called the repulsive case, which leads to all kinds of strange terminology. Yeah, so what if phi is greater than or equal to epsilon on A plus infinity? Well, that's called the repulsive case. The repulsive case. Now, okay. Well, it turns out that then this right inverse that is still a, I mean, this is still a right inverse, right? I didn't assume that I was in the attractive case or repulsive case here. This is in general true, but this B will not have the right properties for our purpose. You need a different B. So, okay, then we need another right inverse. Namely B again, which goes from C. For the moment, I'm just defining it as a map from C0A to C1A, and where BG, T, well, it's almost the same formula, except instead of integrating from A to T, you integrate from infinity to T, right? So It's e to the power Vt integral, and now you start. In fact, I integrate from infinity back to t, which is of course the integral, the minus the integral from t to infinity, and the point is that this integral will exist, e to the power minus Vs gs ds, and phi as before, capital Phi as before. And it turns out that this now has the right properties.
So sorry. So you don't inverse the integral which is defined capital Phi. So same bound for capital Phi, right?
No, for Phi is
okay.
defined.
Okay.
Right.
As before, exactly. Okay.
Yeah. The main point here about Phi is that it's the antiderivative of little phi with, and in fact, e to the power Phi is the thing that has logarithmic derivative little phi.
Okay.
Is that,
okay. Yeah. Right.
Or yeah, that is the main point about this. Right. Yeah. Okay. And yes. And now we do have the right property. Right. Yeah. Again. So for R, yeah, I guess I ran out of space here. So let me write it down here. Right. Yeah, for then in this repulsive case, for again, when we assume that phi is at least r minus 1 times, and again is also bounded in this strong in this sense, and phi, and now greater than or equal to epsilon on a plus infinity for some epsilon. B, yeah, delta minus phi is again map C R bounded to C R minus 1 bounded, and it's the right inverse there, and B, that B from C R minus 1 bounded. Oh yeah, this is continuous linear operator, and B maps this into, goes bounded, A is also is again continuous. Yeah. And you can estimate its or bound its operator norm in right. Okay, so these are the distinguished, yeah, right inverses that we are going to work with. Of course, you can still wonder, what if it's neither repulsive nor attractive? Yeah, I want to say something about that too, because in some sense, repulsive and attractive cases are special. What if we are neither in the repulsive or attractive case? Or what is the right English here? Neither nor, I guess, is the nor in the attractive case. For example, phi could go to 0, right? Phi, if in other words, if phi is infinitesimal, then we are neither in those cases. And but there are ways to get around this. Yeah, ways to get around this difficulty. Yes. Well, okay. One method is we call twisting. One, twisting. This is Joris's notation for something that you think of as a monomial. Let's say funny M, or what is it, Gothic M. Let's say it's 1 times, but it should be a unit. It should never be 0. and then twisting means you multiply delta minus phi on the left with M and on the right with M inverse. And what do you get? Well, it's very easy to check that this gives you that phi changes to phi plus M dagger. Right. So you see that this is a way to change phi into something else. And you can imagine that this might help. If phi, for example, goes to 0, and you take M dagger to be greater than equal to epsilon or less than equal to minus epsilon, then you are still in business. And this is a fairly harmless kind of thing to do. And so another way, and you have to really use this in combination, compositional conjugation. Yeah. I mean, of course, we are going to apply all this when for the case where our phi and so on lie in some Hardy field, the germ of phi, of course, lie in some Hardy field, and then you can do compositional conjugation, which strictly speaking doesn't give you a Hardy field anymore, but it's still isomorphic to a Hardy field. So you simply replace this by this. You think of compositional conjugation as simply composition with a certain function, and so that you are still in a Hardy field. But let me, okay, now instead of the operator, I'm going to write it as a differential polynomial. So delta minus phi corresponds to this differential polynomial, and if you compositionally conjugate with an element theta, what do you get? You get theta y prime turns into theta y prime, and this doesn't change. So you factor out theta, and then you get y prime minus phi, minus theta inverse phi y, yeah? Right, so you see the original coefficient phi gets replaced by theta inverse phi. And typically you do this where, let's say, if phi is infinitesimal, so you are not in attractive or repulsive case, and theta is you do compositional conjugation by something that is small, at least infinitesimal, and that will mean that you multiply phi here by a non-infinite, by something infinitely large. And so you can again imagine that you change this into something that where you are in a repulsive or a attractive case. Of course, there is a price to pay. You introduce an extra factor theta here, but that's not so important. Okay, so that is what I yeah, and all this I explained in the real situation, but everything is also valid in the complexified situation, provided in the complexified situation where phi is also complex. Of course, it doesn't really make sense to say phi less than or equal to minus epsilon or phi greater than to epsilon. What you simply have to interpret this as the real part of phi. In a complexified situation, you replace that condition by the real part of phi is less than or equal to minus epsilon on that half line. And you see, because it's as far as the absolute values of these factors, e to the power phi t and e to the power minus phi s is concerned, that depends only on the real part of. Then the capital phi, of course, will also be complex, and the real part of phi is obtained by integrating the real capital phi is obtained by integrating the real part of little phi, and so and the absolute value of this will only depend on the real part of phi, right? So that is how one translates all this to the complexified situation. Right. So let me see where. Yeah. So now now I can finally start my sketch for the if I can find my notes back. Yeah. Okay. No, there is still one thing to do, I see, because now I want to apply this to where I have a linear operator which is a product, which is a composition of all these order 1 operators. So right. Okay. Now consider, so now consider not just an order 1 operator delta minus phi, but an arbitrary order. Consider any f1 up to fr in, well, yeah, for simplicity, I'm going to assume that they are already bounded. And the operator, and the operator A is delta f1 delta r minus 1 plus fr, which is now an operator from right, C0 bounded. Yeah, if you apply this to an element r times continuously differentiable function, all whose derivatives up to order r are bounded, you see that the result will be a continuous function which is bounded. Right. Now, I'm going to make a big assumption here that A actually splits as a composition of such operators. Yeah, assume A splits as a composition, but I'll write it just as a product, as we usually do when we are dealing with linear differential operators. Yeah, strictly speaking, this is not a linear differential operator, over the differential ring because the coefficients are for the moment only r times continuously differentiable. So, and of course, this is not a differential ring with the usual derivation, since it is the derivative of something here will not be in there anymore in general. But let's say it splits as a composition, right? And I'm going to be a little bit loose now about the domains and codomains of these factors. All this can be made completely precise, and but it's too you know, too much writing to spell out all the details. But just to give you an idea, and we have. Suppose we also have, for each of these factors, a continuous right inverse for each factor delta minus Vj, a continuous right inverse Bj. And here I do specify the domains a. Okay, so this goes for j minus 1 bounded to Cj bounded. Okay. Right. Well, continues again with respect to the norms on these Banach spaces. And well, then that gives you, then we have a continuous right inverse to the whole product, to the whole operator, right inverse. Yeah, you start with inverting delta minus V1, that will be, let me see, is it, or am I doing it the right order? Oh no, it's, I think it's, yeah, it has to be done in this order, you know, B1. Right, if you, wait a minute now, am I doing this right? Yeah, BR goes from CR to CR minus 1, and then from the next one goes from CR minus 1 to CR minus 2, and so on. This brings you, oh no, it's the other way. Wait a minute, I'm now confused. It goes the, this goes from, yeah, no, it should be this one. Ah, okay, no, the problem is that I misindexed. I should index it this way. I know, now it's, wait, now I'm confused again. If you apply B1 goes, now I'm, there's something wrong with the indexing. Maybe this should be delta minus VR minus J, or what? Okay, let me just write this for the moment. C, this goes through 0C bounded to A to CR bounded A. Yes, that's correct. And a right inverse is that if you apply this first, and then you apply this.
Yeah, so I think it's okay.
Oh yeah, I think it is. I think it is. Yeah, with this re-indexing, I think it is okay. Right. So if you first do apply this and then apply that, you get back to where you started with. This, yeah. Right. Okay. Yes. So this gives you a nice right inverse to the operator A. Okay. So now I can finally start with my sketch that I promised. Although I'm not sure how far I will get in it. Yeah, and again, of course, these factors might be not be in the. These factors might be not in the repulsive or attractive case, but then there are all these extra tricks you can carry out to reduce to a situation where you can, where they are repulsive, all repulsive or attractive. And again, all this makes sense in the complexification also, which is crucial actually. So now back to our goal. Yeah, first one more definition, because for an H field K. Yeah, I defined what it means for an H field to be Newtonian, but for inductive purposes, we need a variant of this, R Newtonian. And you can imagine what this means. It simply means for all that you restrict the Newtonian condition to differential polynomials of order at most R for all P in Ky of order less than or equal to R, if the Newton degree, the degree of the Newton polynomial, in other words, is equals 1, then Py, you can solve the equation Py is 0 for some y, some bounded y in K. So you just restricted the Newtonianity property to differential polynomials of order R, and this is useful for inductive, for proofs by induction on R, proofs by induction on R. And it turns out that R Newtonian has already a lot of good consequences. Yeah, Newtonian, at least together with omega free, R Newtonian has typically the same consequences as Newtonian, as long as you restrict yourself to differential polynomials of order at most R. So this is right. So let's now back to our goal. H is a Hardy field. You want to construct, yeah, our goal is to construct a D-algebraic, yeah, a differentially algebraic H-closed Hardy field extension. Hardy field extension. Right. Now, okay. First, there is some very easy reductions. We already know that we can extend H to a Liouville closed Hardy field differentially, yeah, and by just doing differentially algebraic extensions. And yeah, and also you can always join all the real numbers, which is still a real number is always D-algebraic over anything. So we can certainly construct a D-algebraic Liouville closed extension containing R. Yeah. And yeah, in fact, it is useful to even assume that also the cosine and the sine of any bounded element is in there, containing also cos h and sine h for every h. Every h in the for every h in the extension, and this is a non-trivial. This is far less easy, but it's something that we did like 5 years ago. You can make it an omega-free extension, and in fact, it's even in some notes that appear in a seminar, a Paris seminar on ordered structures. So, and even so an extension, such an extension which is also omega-free, which is omega-free. Yeah. Okay, so that's not okay. So assume H has already. So we can assume. So assume H already has all these properties. H has already these properties. Okay. Yeah. Now, of course, if our H happens to be Newtonian, you're done. So let's assume that it's not Newtonian. Yeah. So assume H has already these properties, but is not Newtonian, but is not yet Newtonian. I never Newtonian. Okay, well, then to witness that, well, first of all, first remark, it's enough to show that under these conditions, there is a proper D-algebraic Hardy field extension, yeah? So enough to show H has that, then H has well, then H has a D-algebraic, proper, must be improper D-algebraic Hardy field extension. Yeah. Because then once you have that, you make it again, Liouville closed and so on, and omega-free, and then you do the same thing over again, and keep doing that. And at the end, that will give you something that has to be Newtonian, because you cannot keep deep algebraic Hardy field extension. Right. Yes. So that will be okay. Now the thing is, not Newtonian. You can show that means you have a hole, what we call a hole. Yeah, not not Newtonian, not Newtonian. Then H, and I say what that is a hole, as a hole. And that is, well, it's a triple consisting of a differential polynomial. Yeah. What do we mean by a hole? First of all, it's a differential polynomial over H, which is, let me see. Well, it's not zero, of course. Well, that will actually, M here is what we think of as a kind of monomial, but all it means is really that it's some element of H, which is not zero. And F hat is an actual solution of the differential equation, but it lies not in H itself, but in an extension. So F hat in an immediate H, not a Hardy field extension in general, but an H field extension. The thing is, you see, if you have an omega-free H field, you can always, it always has an immediate Newtonian extension. And so, and okay, F hat an immediate H field extension, but F hat is not in H itself. And yeah, the role of M is to give a bound on F. Yeah, F hat. In this extension, you have this relationship between F hat and M. So M is not too important, but it's useful to have a bound on M, on F hat. Right. Oh, and I forgot the most important one. F hat is a solution of the differential equation. P of hat is zero, right? So actually it's equivalent. If H is not Newtonian, you must have a hole. And conversely, if you have a hole, it couldn't possibly be Newtonian. Because if it's Newtonian and you have a solution of this equation in an immediate extension, it must already be in H itself. But here we are assuming that F hat is not in H. So that is a key point to keep in mind. So really, not Newtonian is the same as having a hole. And now the point is we are assuming we take a hole of minimal complexity. Take such a hole. Oh, yeah. Oh, I guess I can, no, yeah. Yeah, we are going to take a hole of minimal complexity, which means the order of P is minimal. The order of this P is minimal. And then the degree of P in the highest derivative of Y is minimal. And then also the total degree is minimal. So yeah, we take such hole that is minimal. So-called minimal hole, i.e. Yeah, so there are three quantities. The order of P, which I'll call R as usual. And then with respect to, then you can take the degree of P in the last variable, last derivative that occurs. That should then be, and then the degree, the total degree of P. So this is really a triple of natural numbers, and this you lexicographically order. Yeah? Lexicographically ordered. Yeah, so it's really the complexity of the differential polynomial capital P that we are doing a kind of induction on. Right. And yeah, you can, it's sort of a minimal witness, a minimal counterexample to not being Newtonian. And this has very strong consequences. Yeah, of course, since the order, I'm assuming that the order of P is R, it means that you can't possibly have any holes of lower order. And that means that H is automatically R minus 1. Yeah, then H is R minus 1. Yeah, first of all, R is at least 1 because for R is, you cannot have a hole with R is 0. That would mean that P is an ordinary polynomial. And since P is, since H is real closed, it already contains all solutions to ordinary polynomial equations. So R is 0 is impossible. So R is at least 1. And R is at least 1. And H is, and this is a very important consequence of this minimality. Newtonian. Right, and moreover, f hat cannot be a 0 of any differential polynomial of lower complexity, and that in particular means that that you can completely describe the structure of the extension generated by, yeah, so this is the H field or differential field rather generated over H in this immediate extension. You can completely say, describe its structure as basically, I'd have to take the fraction field here. The fraction field of this polynomial ring modulo P. Right, so you take just the polynomials in y up to yr, you mod out by P, and then you take the fraction field. You can make this a differential ring in a natural way. And this is right. The isomorphism here is the one where you let f hat correspond to y, the image of y in this fraction field. So this gives you, okay, another thing you can do is, let me see. Oh yeah. We can also arrange M is 1. Yeah, I mean we have this minimal hole, but there are many ways to change the hole into a form that is more amenable to investigation. Like you can additively conjugate P and multiplicatively conjugate P. You might have to also change M and F in the corresponding way, but there are and you can even compositionally conjugate P. Then you are not, but then you must replace your Hardy field by this composition with this L-inf. So there are many ways to change P and still have a minimal hole. So that's also very useful to keep in mind. Right. Yeah, one thing we can do is, which I forgot to say, for example, you can make M, this bound M here, simply equal to 1. Yeah, we can arrange M is 1 if we want, and in fact, at this point it is useful to do that. Replacing, let's say, P M F hat by what we call a multiplicative conjugate, by P cross M, and then divide M by M itself, 1, and then F hat. You have to change this. I mean, that doesn't change anything, really. But it's, again, for convenience, it's often useful to work with M equals 1. And that means that we are, yeah, so below P1 F hat is our minimal hole. Yeah, just changing notation. I will simply assume that M equals 1. Right. And that means that we are looking for that F hat is infinitesimal, right? So F hat strictly dominated by 1 is the same as saying it's infinitesimal. And so then it's enough. Yeah. So now it's enough to, let me see. Yeah, so F hat is kind of a guide towards what we want. We basically want an element F that it does lie in a Hardy field, but that behaves just like F hat itself. Yeah, so it's enough to find an F strictly dominated by 1, which is Hardian over H. That means it lies in some Hardy field extension over H, such that, first of all, such that, well, I would say well, in some sense, that is much more than we need, right? This is this H field extension generated by F hat in the ambient H immediate extension. And F, of course, this is now the Hardy field generated by F. And of course, the weakest form of isomorphism that you can require is that this is simply isomorphic over H as a differential field. That's actually enough. It doesn't have to be isomorphic as an ordered differential field, but as an H field, but as a differential field, that's enough, because since Pf hat is 0, that will also mean that Pf is 0. So F will definitely be differential algebraic. Right. So, but we are, this is a very ambitious goal. You'll eventually get there after many, many changes the whole and a lot more and a lot of other maneuvering. So at the minimum, we want simply F to be in this much bigger ring, such that F not in H and PF is 0. Yeah, I mean, this is already something that takes effort to find at least a solution in this very big ring. But there we are in a more, how do you say, familiar analytic environment, because we can try to construct things like that by fixed point techniques or fixed point construction. Yeah, for this it is natural to try yeah, I mean, that's fixed point technique. That's somehow very standard approach in theory of differential equations construction. Right. Yeah, so let me see. I now have, yeah, I do have 10 minutes left, but I think to explain what I want to, with a little bit of care, what's going on, I need 20 minutes. So maybe it's better to postpone to next week. And then I will very briefly summarize the last part and then continue and then finish that story. So, yeah, of course, if there are any questions, then
I asked about the definition of whole. Does it need to involve a different degree
no. There are certain ways of making this whole better. Yeah, as I already hinted at, there are additive, multiplicative, compositional conjugation, and you can make it, but you can make it then quasi-linear. You can make P quasi-linear, so then you are really in this Newtonian environment. Yeah, that's right. That is one of the ways that we are going to make P better. Right. Anything else? Yeah, of course. Well, anyway, I'll tell the rest of the story. This sketch. I mean, I basically didn't get anywhere yet in this sketch, but I'll tell the rest on Tuesday.
Yes, a little question maybe. Now, Jean-Philippe Rollin.
Yes, yeah.
Yes. So apparently, this is not a technique in your big book, right? This notion of holes. I mean, or is it?
Right. We didn't. Well, yeah. The term hole doesn't occur there, and certainly the kind of normalizations that we are going to apply, we are going to change this minimal hole into one that is much better behaved. And all these normalization techniques that we had to develop them basically from scratch. There was not too much in our book that we could use.
Okay.
Although, I mean, we use a lot of things from our book, but also there is still a lot missing, as we noticed.
Okay.
Yeah.
Thank you. Thank you. Thanks for your lecture today.
Okay, thanks.